So, yesterday we proved that if 0 to m prime to m double prime is exact, this is exact, then for any module n 0 to home a m prime n m double prime n to home a m n to home a m prime n is exact. So, just wanted to remark that this is the converse is also true, that if this is true, that for any module n this is exact, that will imply this is also exact. One can to say that this is surjective and this is kernelless image, one can take n appropriately m prime and so on and prove this. So, I will simply remark that this is write the modified statement that the sequence is exact if and only if for any module n this is exact. Similarly, the sequence 0 to n prime to n double prime is exact if and only if home for any module m home m n dash to home m n to home m n double prime is exact. Okay. So, this is again usual diagram chasing, the exactly the way we did for the case of exact these proofs last time. So, suppose you take a let us see be a class of A modules, okay. Suppose you have a suppose your A is a field K, you can think of C as finite dimensional vector spaces over K. So, you are basically looking at from the category of A modules, we are taking a subclass. Okay. A numerical function lambda from C to n is said to be additive if for any exact sequence, short exact sequence, so this I will write like this 0 to m double prime to 0, we have lambda of m prime minus lambda of m plus lambda of m double prime is 0. Okay. So, as I said, if you want to have a look at this example, suppose your ring A is a field and C is set of all finite dimensional vector spaces over A. Okay. Then you can take this lambda as dimension. If you take lambda as dimension, then it is a numerical function. Will it be an additive function? Suppose you have V1 to V2 to V3 to 0. If you have a vector space, if you have 3 vector spaces, finite dimensional vector spaces, okay, can we say that dimension of V1 minus dimension of V2 plus dimension of V3 is 0? This is exact, yeah. If this is exact, what we know is that V3, so this is surjective map, therefore V3 is isomorphic to V2 modulo kernel, which is the image which is isomorphic to V1. So, you can write this as isomorphic to V2 mod V1. So, therefore, dimension of V3 is, it is basically rank nullity theorem. Okay. So, rank nullity theorem says that this is, if we take C to be, if your ring A is a field and C is set of all finite dimensional vector spaces over A, then the lambda equal to dimension of V is an additive function. Suppose I have a, suppose C be a class of, I mean now I am talking about general, some class over a general ring, be a class of modules of A modules, and lambda be an additive function. Okay. Suppose I have a exact sequence. So, I have an exact sequence like this, M1 to M2 Mn minus 1 to Mn to 0. Okay, so call this phi 1, phi 2, phi n minus 1. Lambda is given to be an additive function, and this is an exact sequence. Here n could be any finite number. Can we, or would you like to say something about lambda? Modules in C, for example. I am talking about modules, these are all M1, M2 etc. are all modules in C. Okay. So, first of all, this is something that I probably mentioned it in some time back. See, if I have an exact sequence like this, I can split this into a lot of short exact sequences, right. So, this is, so 0 to M1 to M2 to image of phi 2 to 0, right. This is an exact sequence. Now, I have image of phi 2 which is also same as kernel of phi 3 to M3 to image of phi 4 to 0, right, and so on 0 to. So, I have image of phi n minus 1 is Mn itself. So, we can talk about the previous image phi n here. Image phi n is phi n minus 1, this is Mn to 0 to Mn minus 1 to image of phi n minus 2, which is same as kernel phi n minus 1. Okay, I have these are all short exact sequences arising from here. Okay, this sequence is exact. Then I have several short exact sequences. Suppose your function lambda is additive on C. What can we say here looking at this one? Lambda of m1 minus lambda of m2 plus lambda of. So, for that we need one condition, that this is also here. We have started by taking m1, m2, etc. We are just taking a class. We are just taking an abstract class. So, we do not know if I take m1, m2 and so on and look at an exact sequence like this, that need not necessarily imply that all these are in that class. Okay. So, therefore, if I assume that all these are in this class, then I can apply lambda, the property of lambda on each of them. Lambda m1, lambda of m1 minus lambda of m2 plus lambda of m3 is 0. Sorry, lambda of this is 0. But now from here, see, lambda of this plus lambda of m3 plus minus lambda of this minus lambda of m3 plus lambda of image phi 4 is 0, or in other words, lambda of image phi 2 is same as lambda of m3 minus lambda of image phi 4. But now image phi 4 I can get from the next exact sequence. I can keep going down. What do I get? So, okay, so let us now complete this proposition, and then this is suppose there is an exact sequence as given below, such that image phi I is also in C for all I. Then I will reserve that conclusion, let us see what it is, and then we will come back and write that. What we have from the first exact sequence, we have lambda of m1 minus lambda of m2 plus lambda of image phi 2 is 0. Now, from the second exact sequence, image phi 2 is lambda of m1 minus lambda of m2 plus image phi 2 is lambda of image phi 2 is lambda of m3 minus lambda of image phi 4. This is equal to lambda of m3 minus lambda of image phi 3, sorry, phi 4. But what would be image phi 4? From the next one, it will be lambda of m4 minus lambda of image phi 5. Yeah, lambda. So, this is 0, that implies lambda of m1 minus lambda of m2 plus lambda m3 minus this is lambda of m4 minus of minus plus lambda of image phi 5 equal to 0. Sorry, it will be, yeah, it will be 6. this will be next will be image 0 to image phi 4 equal to kernel phi 5 to M 5 to image phi 6, it will be 6 itself. Yeah, you are. Sorry, no, we do not need. See, at every time now image phi 2 is kernel phi 3. Oh no, this should be 3, image phi 3 itself. Yeah, yeah, this should be 3 and 4. See, from M3 the image, the map starts from M3 is phi 3. So, the M2 image phi 3. So, ultimately what are we going to get? Lambda of M1 minus lambda of M2 plus minus 1 power n lambda of Mn, or in other words summation minus 1 power I lambda Mi is 0, I from 1 I minus 1. So, this is n minus 1 to n minus 1, sorry 1 to n. So, let us complete this. This is I from 1 to n minus 1 minus 1 power I minus 1 lambda of Mi equal to 0. If I have an additive function that, now additive function means if you take a short exact sequence, the alternate sum of the corresponding numerical values is 0. If I have an additive function and if I have a exact sequence coming from the class of modules where lambda is an additive function, then what this says is that you have alternate sum can be extended to long exact sequence, not long exact sequence, this exact sequence which is not necessarily the short exact sequence. Okay. One typical example is if I take a vector space A, sorry, if I take field A and finite dimensional vector spaces over A. Okay. So, now let us move on to study a very important classes of modules called tensor products. Okay. Let A be M n be finitely M n be A modules, a bilinear map F from M cross n to P, where P is an A module, is okay. A map F from M cross n to P, where P is an A module, is said to be bilinear if for each x in M, y mapping to f x y is linear, and for each y in n, x going to f x y is alinear. In fact, is said to be A bilinear if, or in other words, for each x1 x2 in M, y1 y2 in N, A B in A, f of x1 plus x2 y is f x1 y plus f x2 y, f x y1 plus y2 is f x y1 plus f x y2, and similarly f of a x comma ax comma y is a times f of ax comma y is a times f x y, f of x by is b times f x y. The usual definition of bilinear, linear in each variable. Okay. So, suppose I have a module M, modules M and N. Okay. Our aim is to define what is called a tensor product of M and N. This is tensor product of M and N is or the tool tensor product is a very important tool in the homological algebra. Homological algebra or the methods of homological algebra are applied in every part of commutative algebra, algebraic geometry and so on, even in analysis and so on. These are very important. Analysis, the approach is slightly different, but this is a very important module, the tensor product of M and N. So, I mean, how do we construct this? What do we do is, we first look at take the free module, be a free module, or I'll just write let f be equal to A M cross N, or this is also I'll write in this form. What does this mean? I take as many copies of A as the number of elements of M and N. So, if M and N are infinite or even M is infinite, this is a direct sum of infinitely many copies of M and N, infinitely many copies of A. So, for each x comma y, I have a E, you can think of an element E in E x comma y in F. That is the element where the coordinate with respect to x comma y is 1, rest of them 0. See, there are as many copies of A as the number of elements here. So, this free module F, you can think of this as generated by the set E x y, where x y is in M cross N. It is generated by this set. For example, if M is Z2, to take a simple example, N is Z3, okay. this f will have 6 elements, not 6 elements, this will have 6 copies. Your A will be, f will be generated by E10, E00, E10, E01, E11, E02, E12. Now this E00 is, this is isomorphic to A6. This is 1 0 0 0 0. I mean the 0, the first entry is non-zero, the rest of them is 0. I consider the first copy of A corresponding to the element 0 comma 0. The second copy of A as element corresponding to this one, and so on. So this is, I take this free module. Now what do? I want to see, my aim is to say that every bilinear map from M cross N to a module P filters through M tensor N. M tensor N, I am trying to construct the unique object with the universal mapping property that every bilinear map from M cross N to an A module P filters through or extends to M tensor N to P. So first what I will do is, on this one I take a submodule, okay. Let D, yes, I am taking, do you understand this definition? Okay. I am taking as many copies of A as the number of elements of M cross N. Okay. So here I am just indicating what is E. See, when I say in the standard vector space Rn, when we say E1, this is 0, where this is 1 on the first entry. So if I write this M cross N like this, 0 bar 0 bar, 1 bar 0 bar, 0 bar 1 bar, 1 bar 1 bar. So here these two bars are different, one should be careful with that, 0 bar 2 bar, 1 bar 2 bar. So for each element I have a copy A. Okay. So this is the basis for that. Now for that entry is for the first, this is the first entry, let us say. Then I have a corresponding copy of A here. So I will have 1 0, this is the generator of that part, that copy, that is exactly I am denoting it by E00. So here I am just following this notation here, that is how. Okay. So for each element xy I have a generator EXY. My idea is to create a module such that any bilinear map from M to N, M cross N to P filters through M tensor N. So let us look at this DB, the submodule generated by the elements x1 plus x2 comma y minus x1 comma y minus x2 comma y in F. Sorry? Yeah, I am not, this is not the only element. Okay. See, looking at this, immediately you will have a tendency to say that this is 0. What is our f? For each element in M cross n, I have E there. So, I am in fact, okay, so I should probably write like this: E x1 plus x2 comma y minus E x1 y minus E x2 y. This, now you understand that they are different, right. Similarly, I will look at E x y1 plus y2 minus E x y1 minus E x y2. Similarly, E a x y minus a times E x comma y, E x a y minus a times E x comma y. So, for all x1, x2, x in M, y1, y2, y in N and a in A. So, now let us just set some more notation. See, how does any element of f look like? Any element of f is a finite linear combination of elements of the form E x y, right. So, I can any element, so if I take an element M in f, M will be a I E x I y I, some finite linear combination like this. Okay. Now, in the module M cross n, there is an element called of the form a I x I y I. Okay. So, there is an element corresponding to this, I have an element E of this summation. These two are not the same. This is an element in F which is a linear combination of some basis elements, while this is a basis element. Okay. So, moreover, you can so that difference you should keep in mind. Now, so my D is all the elements of this form, and I take my module, let T be equal to F modulo D. I take T to be F modulo D. This looks like to be a highly abstract, horrendous set of elements here or the module, but it is not so. Once we use this, we will understand, we can easily see. Yeah.
And the first time you taken and such that is but that might not be because we take AI with the X size.
Yeah.
Then we get different elements.
Sorry?
We get different elements.
Which one?
If we say E of AI xi comma yi, one element is this, and similarly if we take AI within the yi, will get differently.
No, this is I am talking about this ai dot xi, this as an element in m cross n.
Sir, in the first line.
This one.
Yes, sir.
Huh.
If we multiply.
Yeah. This, that will be different from this one. Is that what you are saying?
Yes, but the definitions.
No, here I am no, I am not talking about elements in D or anything. I am just talking about simply representation of elements in F. See, F, the definition has enough things to get confused. You can't, you can simply accept that F is this, but to understand that it takes little more effort. That is why I tried to explain this part. What I am trying to say here is that I have any element of F looks like this, okay. This is different from this element, that is all I am trying to say. There is a basis element corresponding to this element in the M cross n. Each xi yi is in M cross n, but you take the corresponding element in F and take the linear combination there, and take the linear combination M cross n and look at the corresponding element, they are different. You have to, but once you come to D, what do we have? When we, D is submodule generated by elements of this form. So, in D, modulo D, these two are equal. Okay, let me just take simple example. I have my M is AXY, okay. So, I have this, so I have EAXY, well not this same as the other one, let us see what it is. This is
this minus m will belong
sorry, what I want to say is, I have M as this and I have A times XY, okay. Now, A times EXY modulo D, see what are the elements in D generated by A times xy minus, or E of AXY minus E of AX comma y minus A times E of xy. So, if I take this is E of AX comma y minus this is 0 in F mod D, right, or in other words if I take the corresponding bar, this is same as in F mod D, okay. Similarly, if I take E in F, these two are not the same, because this is a basis element, this is a basis element. You cannot have one as a scalar multiple of the other. But then modulo D, these two are same, that is how we have constructed. Similarly, what can you say about E x1 plus x2 minus comma y? This is same as E x1 comma y minus E x2 comma y, sorry plus in F mod D. So, now let me define T, and we have correspondingly using these properties I can extend this further in f mod d. This is same as summation, yeah, this one. Okay. So, let T be equal to f mod d. Suppose I have a bilinear map f from m cross n to p be a bilinear map. What does that say? It says f of x1 plus x2 y is same as f of x1 comma y plus f of x2 comma y. Okay. And f of and so on, I won't write down all the conditions, f of x comma y1 plus y2 correspondingly and so on. Once I have this map, this induces a map, let us say f tilde from f to p. What is my f is free module on m cross n. So, what I do is f tilde of E x comma y is f of x1. E x y is a generating set for f. It is a basis for f. So, I define f tilde of this, or if you want to define on a general element, summation a I E x I y I same as summation a I f of x I y I. Okay. This induces map from f induces map from f to p. Now, our aim is to say that every bilinear map filters through the tensor product, or in other words I can extend it to a map from m tensor n to p. So, here I have this map mn to p. Now, I have a natural inclusion here to f, and this I have a map from f to p. I am looking for something here t to p. So, I have this is f tilde, okay, and I am looking for some f prime which again comes from f. See, t is a quotient of f. Suppose I have a module homomorphism, let us call it k1 to k2, okay, and let us say L is a submodule of k1. Okay. When can I say that it will induce a map from here to here? If L is contained in the kernel of f, see, then L is naturally killed by f. Then you can always extend this map, or this f will induce a map from here to here. So, therefore, now I have a map from f to p. To say that there is a map from t to p, if I say something, I am done. What should I say? That D is contained in the kernel, but is that so? F is a bilinear map. Okay. So, if I take contained in the kernel of f tilde, what is f tilde of E x1 plus x2 comma y minus E x1 comma y minus x2 comma y. If I take an element in D, this will be 0, because this is by definition, what is this? This is f of x1 plus x2 comma y minus f of x1 comma y minus f of x2 comma y, right? F tilde, well, so this is check, f tilde is a bilinear, a linear, sorry. Yeah, that's f tilde is linear by definition, in the sense that, see, it is like I am defining, this is exactly like the way I define linear transformation from a vector space with a given basis to another vector space with a given set of elements. So, here I am defining this form a basis for f. So, I am defining it on the basis, or in other words, to make a precise definition, it is f tilde of summation a I E x I y I is summation a I f x I y I. So,
this definition also implies that f tilde of E x1 plus x2 y is equal to f x1 plus x2 y, which is equal to f x1 y plus f x2 y,
yeah,
which will be equal to f tilde of E x1 y plus f
what are you saying? F tilde of
E x1 plus x2 y.
that is exactly what we are saying. In the on elements of, see, this is, yeah, this is equal to f of f x1 y plus f x2 y,
Which is equal to f tilde of E x1 y plus f tilde of E x2 y, which is not true in general. I mean,
no, that's I mean there is no problem, this is exactly what we are saying. This is equal to f tilde of E x1 y plus f tilde of E x2 y, right? Or in other words, f tilde of E x1 plus x2 y minus x1 y minus x2 y, this is 0.
no, so why are we taking x1? Like, we haven't proved that f of E something plus E something is equal to.
It is not, I am not saying this need not be 0.
You are taking that to the left hand side, then you are taking minus inside, and
F tilde is, I mean, by definition f tilde is linear, that is how I am defining f tilde. Okay, so let me write down the definition of f tilde here. How does any element of f look like? So, let us take m to be in f, m is of the form summation a I E x I y I, okay. I define f tilde of m to be equal to summation a I f x I y I. This is, so f tilde is I mean linear by definition. This is exactly how we define in the vector spaces also, right. We define it on a basis elements and extend it linearly to the whole vector space. This is exactly what we are doing here. So, therefore, this is 0. So, what we have shown is that f tilde of A is 0 for all A in D. This implies f tilde induces a map f prime from f mod d to p. Now, let me denote this by, so this is, see here f tilde is only a linear, f prime, okay, we do not have to, we have not defined what is called bilinearity here, but f prime of x1 plus e by definition itself, e of x1, okay, let me just say that this is what we call it as t. I have already defined this. We will prove that this is this t is uniquely determined up to isomorphism, in the sense that if I have this universal mapping property that any bilinear map from M cross N to a module P, it filters through another module T prime, then T prime has to be isomorphic to T. We will complete the properties of tensor product in the next class.